Good evening. Thank you for following me on Twitter. I would also like to welcome everyone who has joined me over the past month on our web TV channel. It is much appreciated. In this programme, all times are given in universal time and measurements are non-metric. Venus, Mars, Jupiter and Saturn are now on view, and with a total eclipse of the Moon taking place on April the 15th, in this month's programme we take a look at how best to make observations of the planets. There are two types of telescope: the virofractor, which uses a lens to collect the light of the object on view, which is focused down the main telescope tube into the eyepiece where the image is magnified. For planetary work, a 4-inch refractor is the smallest useful size, which is reasonably portable. Larger refractors are superior, although better suited to being housed in an observatory. The refractor telescope uses a main concave mirror to collect the light of the object. There are two types: the Newtonian, which reflects the light of the object back up the main tube onto a small flat mirror angled at 45 degrees, where it is directed out of the side of the telescope into the eyepiece. And the Cassegrain, that uses a combination of mirrors and lenses to fold the light and form an image. Usually the eyepiece is situated at the bottom end of the telescope in front of an opening in the primary mirror. The minimum useful size for a reflector for planetary observations is 6 inches. Reflector telescopes have the advantage over the refractor because they collect more light and can resolve finer details. In terms of magnification, the general rule is 50 times per 1 inch of a telescope aperture. Therefore, under excellent seeing conditions, a 3-inch refractor will allow you to use a magnification of 150, while with an 8-inch telescope, a power of 400 is possible. Your observations should be kept neatly in an astronomical notebook. The location of your observing site should be recorded, including the latitude and longitude, if at all possible. No observation is useful unless it carries the observer's name, the time in universal time, or GMT, telescope, magnification, and seeing conditions. For this, the scale devised by the late E.M. Antoniadi is suitable. It ranges from 1, near perfect conditions, down to 5, very poor. There are two pieces of advice I can offer. Firstly, do join your local astronomical society. They have experienced observers on hand to answer your questions, and many groups have telescopes for you to use to see the planets in detail. Secondly, don't hurry an observation, and always record it as soon as it has been completed. Never place any reliance upon an observation under rushed or poor conditions, and above all, never give way to wishful thinking. Only record what has been seen with certainty, and beware of jumping to conclusions. If you go to your telescope expecting to see dark markings on a planet, you might record them even though you have not actually seen them through the telescope. The solar system is made up of a sun in the centre, and in order of distance we come to the 4 rocky planets: Mercury, Venus, Earth and Mars. Then there is a wide gap filled with over 3,000 chunks of rock we call the asteroid belt, after which we arrive at the 4 giant planets: Jupiter, Saturn, Uranus and Neptune. Here is a combined image of all 4 of the main planets, taken in March by Jason Higley, who lives in Orlando, Florida. Jason was using a 6-inch Newtonian reflector. The planet Venus is the second planet out from the Sun, lying at a mean distance of 67 million miles, and is often referred to as the Earth's twin because its diameter of 7,700 miles is similar to our own. It is a strange world. Its south pole is uppermost, so it is not only upside down, it rotates in the opposite direction to the rest of the planets. Also, the planet's actual rotation of 243 Earth days is longer than the planet's year of 224.7 days. Venus is covered in a thick atmosphere of mostly carbon dioxide clouds that reflect much of the sunlight reaching the planet's surface and traps in the sun's heat. The planet therefore has a hostile environment. It rains sulfuric acid droplets, the atmospheric pressure is 90 times greater than that of our own, while the surface temperature is a staggering 485 degrees centigrade. Like Mercury, it stays in the same region of the sky as the Sun, but the angular distance between it and the Sun can attain 47 degrees. This means that Venus can remain visible for as much as 5.5 hours after sunset and 5.5 hours before the Sun. The planet Venus is now visible in the eastern sky before sunrise, fading slightly from magnitude -4.3 to -4.1. From April to October, observers in the southern hemisphere will have the best view of the planet, which rises more than 3 hours before the Sun. Observers in the northern hemisphere will see the planet rather low in the sky. During this time, the planet's apparent size shrinks while its phase grows to that of full. On August the 18th, Venus will be extremely close to the planet Jupiter in the dawn sky as it passes to the north of the planet, and the two objects will make a nice pair before and after this date. Both planets lie in the bright open cluster Messier 44, known as the Priapus, in the constellation of Cancer the Crab. Superior conjunction occurs on October the 25th, when the planet will be too close to the Sun to be seen. Unfortunately, Venus is a telescopic disappointment because the true surface is hidden by a dense cloudy atmosphere. Venus will not bear high magnifications, and a sharp view with a low power eyepiece is to be preferred to a larger blurred disk. A 3-inch refractor will show the planet's phases reasonably well, while a reflector of 8 inches or more is preferred to do some useful work. Of course, if you are a keen digital photographer, you may have an ambition to buy or make your own large reflector, which will allow you to do useful work. Two amateurs who have done just that are Trevor Berry of Broken Hill, Australia, who uses a purpose-built 16-inch Newtonian, and Daryl Malilka of Selix Beach, South Australia, who uses a Celestron 14-inch. Here are some of their images of Venus. Daryl took these on January the 25th, 2014, showing the planet's slender crescent. And here are 3 images of the planet taken by Trevor Berry from November the 16th to the 18th, 2013, using an ultraviolet filter to bring out the elusive cloud detail. Dusky shadings in the cloud tops can be better seen by using a blue filter, although they do not appear often. One such example is the cusp caps, now known to mark the poles of Venus, which have been recorded by most observers. The caps are not always on view, and neither do they lie exactly at the cusps. It is useful to record whether either cap is visible, or if so, what form it takes. Most planet observers adopt a scale of 2 inches as the planet's diameter and carefully depict the planet's phase. Intensity estimates for surface features are useful, preferably using a scale from 0 to 5, where 0 equals white and 4 equals more definite shadings, somewhat rare. At the beginning of April, Venus is at half phase. Astronomers call this ditch to me. Useful observations of Venus are now focusing on what we call the Scrotus effect. In August 1793, the German moon and planetary observer John Scroter discovered that the observed time of half phase did not correspond to the predicted time. Scroter saw some phase deformity of the southern limb of Venus, which remained concave until about 8 days before or after the predicted date. In 2015, the calculated date of dichotomy are the 6th of June and 25th of October. The actual date of dichotomy is not easy to determine because of the apparent projections of the cusps. The best method to estimate the phase is to draw Venus as it is seen through the eyepiece and then measure the phase afterwards from the drawing. The third planet out from the Sun is the Earth, which along with our Moon can be considered as a double planet. The Moon is 2,927 miles in diameter and orbits our Earth once every 27 days. The Moon's appearance in the sky changes daily, showing a series of phases, from full moon to new moon and back again, and many observers are able to make out the depiction of the man in the moon with the unaided eye. There are a lot of things that the amateur astronomer can view with binoculars or even a small telescope: the many craters, seas, mountain ranges, rills and domes. To cover the topic of how best to observe these features requires a TV show all by itself, which is beyond the scope of this programme. Instead, I will concentrate on this month's total eclipse of the Moon, which will take place on April the 15th. A lunar eclipse occurs when the full moon passes through the Earth's shadow in space. The shadow has two regions, an inner dark area known as the umbra and a much lighter outer area known as the penumbra. A total eclipse of the Moon is the most impressive as the Moon's disk changes colour to copper orange, even red, as it passes through the umbra. This is an ideal opportunity for photographers. The eclipse will be visible in its entirety from the western and central United States, Canada, West and South America and the eastern Pacific Ocean. From the United Kingdom, it will have barely entered the outer shadow, known as the penumbra, before British moonset occurs. The edge of the Moon first enters the inner darker umbral shadow at 05 hours 58 minutes universal time, with the whole lunar disk being covered by 07 hours 7 minutes. Mid-totality occurs at 07 hours 46 minutes, and the Moon end starts to emerge from the umbra at 08 hours 25 minutes and is completely free of the umbra by 09:33 minutes. Totality will last for 1 hour and 18 minutes. The next total eclipse of the Moon, visible in the United Kingdom, will be on the 28th of September 2015. As the Moon moves along its celestial path, it passes in front of the stars and occasionally a planet, an event which astronomers call an occultation. This month, on April the 17th, the Moon will occult the ringed planet Saturn as seen from South America. The event begins at 05 hours 9 minutes UT. As seen from the UK, Saturn will be close to the upper left of the Moon from 10 PM onwards, making an ideal photo opportunity. This year, Australian sky watchers are being treated to the ringed planet Saturn slipping behind the Moon, not once but 3 times. This next occurs on May the 14th. Australians living in the southern states will see 3 complete occultations of Saturn. People living in Darwin will see 1 complete occultation on the 4th of August, and people living in Perth will see an extra graze on the 11th of June. The planet Mars lies in the constellation of Virgo above the bright star Spica and is at opposition on April the 8th, when it will be due south at midnight and at its brightest magnitude -1.5. The apparent diameter of the planet is currently 15 arcseconds, which is not very great, and the North Polar Cap is tilted towards the Earth, so that it is now summer in the planet's northern hemisphere, which will last until August the 17th. The celestial path of Mars during the remainder of 2014 takes it into the constellation of Libra in August, when it will lie 3.5 degrees south of Saturn on August the 27th. The planet then moves into Scorpio in September, Sagittarius in October, and then Capricorn as the year comes to a close. Mars is the 4th planet out from the Sun, lying at a mean distance of 141.5 million miles, and takes 687 days to go around the Sun once. The planet is smaller than ours, being only 4,200 miles in diameter. Mars also has a day similar to ours, lasting 24 hours 37 minutes. The surface of the planet has desert-like conditions with various interesting features such as craters, canyons and a small number of shield volcanoes. Mars is a difficult planet for small telescopes. It comes to opposition only in alternate years, and in general, useful observations can be made for a few months to either side of opposition. one really needs a telescope of over 8 inches aperture to do useful work. Owing to the smallness of the disk, Mars is the one planet which a really high power should be used whenever possible. It is best to select a definite scale for the drawings. Here again, 2 inches to the planet's diameter is ideal, and the phase, which is often considerable, should never be neglected. This can be worked out beforehand from yearly tables and with disk outline prepared. These images were taken by Trevor Berry this year using his 16-inch telescope on the 24th of February and 20th of March 2012. And here is a set of images of Mars taken by Daniel Gaspari using a Celestial 14-inch reflector at his observatory in Bologna, Italy. The objectives are to detect any changes in the shapes and intensities of the classical dark markings of Mars and the presence of new features. These changes are related to the appearance of dust storms, yellow clouds, to map the extent and shape of the polar caps, to note their brightness and definition, and to observe any interior details or detached portions. Finally, to chart the positions and movements of the Martian dust storms, and to document the occurrence of seasonal or white clouds. Before starting to draw Mars, it is wise to spend some time in surveying the planet until the eye has become thoroughly adopted. When the drawing is begun, the polar cap and main dark areas should be sketched. This should be done as quickly as compatible with accuracy, because Mars is rotating on its axis and there is a slow but perceptible drift of the markings across the disk. Minor details can then be added at leisure. When the drawing is complete and you are satisfied that nothing has been missed, written notes should be added about colours, intensities and any features of special interest, notably the clouds. With apertures of 6 inches or more, examine Mars visually with coloured filters. Filters reveal details of the structure of the Martian atmosphere, unobtainable by observation using a plain eyepiece. The red as well as yellow and any orange filter will be of help in intensifying the dark markings and in enhancing the visibility of faint desert details. Do not expect to see too much. At first you may be able to make out nothing apart from a few dark areas and the white polar cap, but as you gain experience you will see more and more. The planet Jupiter can be seen in the eastern sky as a brilliant yellow star in the middle of Gemini, the twins, as soon as darkness descends, and is best seen by observers in the southern hemisphere. It continues to get lower in the sky until on July the 24th, Jupiter will be in conjunction with the Sun. The planet then becomes visible in the morning sky from the beginning of August, when it will be extremely close to the more brilliant planet Venus in the constellation of Cancer the Crab. Jupiter is the 5th planet out from the Sun, lying at a mean distance of almost 483.5 million miles, and is a giant planet of our solar system. It has a diameter of 88,700 miles and takes about 12 years to orbit around the Sun once. Because Jupiter is so massive, even small telescopes will show the horizontal cloud bands across the planet's disk, while binoculars will reveal the planet's 4 Galilean moons, Io, Europa, Ganymede and Callisto, as they slowly change positions around the planet. Most of our long-term knowledge of Jupiter's surface features is due to amateur astronomers. The disk has lots of detail, and a telescope of 6 inches is enough to do useful work. The average rotation period of Jupiter is 9 hours 50 minutes, therefore disk drawings should be made as quickly as possible, as the rate of spin is rapid and the drift of the markings is very obvious. The drawing should be completed within 10 minutes at most with regard to the major details. Minor ones can be filled in more slowly without altering the general framework. The colours seen should then be noted, and also the relative intensities of the various belts, spots and zones. Here are two images of Jupiter taken by Trevor Berry. The first is from November 2010, showing the Great Red Spot. A very important part of the Jupiter program is the taking of transits. A feature transits when it passes across the planet's central meridian, that is to say, the line passing through the two poles and the centre of the disk. The polar flattening enables the central meridian to be found easily, and this flattening should never be neglected when the drawing is made. Transit times should be estimated to the nearest minute, and accurate timing is essential. It might seem a difficult task to make the estimates with sufficient precision, but with a little practice it becomes strangely easy, and it is possible to make many transits in the course of an hour or so as the markings drift steadily across the planet's disk. Here are two images of Jupiter taken by Daryl and Patricia Malilka. These transits are important because they allow the longitude of the feature to be calculated and hence the rotation periods to be derived. It is easy to work out the longitudes from the tables given in the handbook of the British Astronomical Association or other infirmaries, which give the longitude of the central meridian for every hour. The only maths involved is simple addition and subtraction. On this image of Jupiter, taken by Trevor Berry, the information about the planet's System 1 and System 2 longitudes, along with the telescope equipment, can be seen at the bottom. As the equatorial zone, System 1, rotates more quickly than the rest of the planet, System 2, two sets of tables are necessary, and there must be no confusion as to which set is to be used, otherwise the results will be most strange. Remember that System 1 is bounded by the northern edge of the south equatorial belt and the southern edge of the north equatorial belt. So far as the Galilean moons are concerned, the most useful work is to make careful timings of the transits, immersion, emersion at the planet's limbs, shadow transits, occultations and eclipses. These observations help in improving our knowledge of the movements of the satellites. The planet Saturn is the sixth planet out from the Sun, lying at a mean distance of 886 million miles, and is surrounded by a magnificent ring system that can be seen through small telescopes. Saturn is smaller than Jupiter, its diameter is 75,100 miles, and the planet takes 29.5 years to travel once around the Sun. Saturn lies in the constellation of Libra the Scales, shining at magnitude plus 0.4. During April, the planet rises 2 hours before the Sun and is visible low in the southern sky before reaching opposition on May the 10th, when it will be best placed for observation. At that time, the apparent diameter of Saturn will be 45 seconds of arc, which is comparable to that of Jupiter at 37 seconds of arc. Saturn lies in Libra during the rest of this year, when its celestial path takes it eastward to a stationary point in July. It then moves in the opposite direction, heading towards the nearby constellation of Scorpio. However, from mid-November, Saturn will be too close to the Sun to be seen. These images of Saturn were taken recently by Trevor Berry, along with Daryl and Patricia Malilka, which show the planet really well. Saturn is in some ways a convenient planet. It bears high power as well, even better than Jupiter, and although there is not generally much surface detail, there is always a chance of making a startling discovery. Like Jupiter, the planet rotates relatively quickly, so that a day here lasts 10 hours, 15 minutes long. The rareness of well-defined detail means that surface transits are difficult to take, but whenever possible, they should be observed in the same way as for Jupiter. For this work, a telescope of at least 10 inches aperture is needed. It is also valuable to estimate the colours and intensities of the various zones of the planet, as unexplained cloud storm features occur from time to time. The lovely rings are nicely on view this year, which can be glimpsed with a refractor telescope of 2-inch aperture. However, the larger the telescope, the better the view. Look out for the thin black partition in the rings between the outer ring A and the inner ring B, which was first identified by the Italian astronomer Giovanni Cassini at the Paris Observatory in 1675. Cassini's division is easy to see when the rings are fairly well open, as they are at the moment. Estimate the colours and intensities of the rings, comparing them with each other and also with the disk, using a scale from O, white, to 10, black shadow. When the drawing is made, take great care to put in the shadows very accurately. Globe upon rings, rings upon globe. The shadow on the rings is important because any irregularities may give a clue as to the structure of the rings themselves. Saturn is at its most interesting, though least beautiful, when the rings are edgewise on, for this will not occur again until 2025. Any 3-inch refractor will show Titan well, and with a 12-inch reflector you will be able to see all of the major satellites except Phoebe. The main work with regard to the moons is in magnitude estimation. Convenient stars may be used as comparisons. Be sure to identify them correctly. But when there are no stars to hand, as often happens, the only real solution is to adopt a constant magnitude of plus 8.3 for Titan and work from that. Errors are bound to be introduced, however, this method is better than nothing. I am most grateful to Daryl, Patricia and Trevor Barry from Australia, who supplied the majority of this month's planetary images. For those of you who are familiar with taking digital images of the planets, here is the information of their equipment and observing programs. Trevor Barry uses a 16-inch Newtonian reflector. He told me his telescope is mounted on a German equatorial mount that he designed and built. This is an image of Trevor and his telescope, an image of his Peltier cooler on the primary mirror, and another image showing his latest imaging train. That consists of a JMI motor focus, Sabert 4x Barlow lens, filter wheel with red, green, blue, ultraviolet and infrared filters, and an ASI 120mm camera. Note the modified 8x50 finder, which Trevor has fitted a camera along with a Telerad and a standard 8x50 finder. Trevor's images goes to the Venus, Mars, Jupiter and Saturn sections of the British Astronomical Association and associated lunar and planetary observers in Japan. He is also involved in several amateur and professional collaborations, the longest being an ongoing involvement with the Cassini spacecraft team via George Fisher at the Austrian Academy of Science. Daryl and Patricia use a standard Celestron 14-inch reflector with some self-made modifications and describe themselves as roving imagers. They drive to areas in the bush, not too far from Adelaide, to photograph the planets, camping in their van on a regular basis. They also supply images to the British Astronomical Association and work closely with George Fisher from the Saturn Cassini team. Daryl told me they provide images when requested to various research institutions, such as recently to the University of Leicester's Radio and Space Plasma Physics Group in their Department for Physics and Astronomy. A particular highlight for Daryl was being asked to test and assist with the software development of a new CMOS-based camera designed for planetary imaging, the ZW Optical ASI 120mm. Daryl and Patricia were the very first to receive one of these units from outside mainland China. Clearly, All of the splendid photographs taken by this month's contributors are a fitting tribute to the Year of the Planets. That's all we have time for this month. Please visit our website, Vimeo, where you can watch all of the past shows of Astronomy in Space. And if you like this program, please share it with your friends and members of your local astronomical society. When I come back next month, we'll be taking a look at the constellations of spring. Until then, goodbye for now. There are two pieces of advice I can offer. Firstly, do join your local astronomical society. They have experienced observers on hand to answer your questions, and many groups have telescopes for you to use to see the planets in detail. Secondly, don't hurry an observation and always record it as soon as it has been completed. Never place any reliance upon an observation under rushed or poor conditions. And above all, never give way to wishful thinking. Only record what has been seen with certainty and beware of jumping to conclusions. If you go to your telescope expecting to see dark markings on a planet, you might record them even though you have not actually seen them through the telescope. Back up the main tube onto a small flat mirror angled at 45 degrees, where it is directed out of the side of the telescope into the eyepiece. And the Cassegrain that uses a combination of mirrors and lenses to fold the light and form an image. Usually the eyepiece is situated at the bottom end of the telescope in front of an opening in the primary mirror. The minimum useful size for a reflector for planetary observations is 6 inches. Reflector telescopes have the advantage over the refractor because they collect more light and can resolve finer details. In terms of magnification, the general rule is 50 times per 1 inch of the telescope aperture. Therefore, under Good evening. Thank you for following me on Twitter. I would also like to welcome everyone who has joined me over the past month on our web TV channel. It is much appreciated. In this program, all times are given in universal time and measurements are non-metric. Venus excellent seeing conditions, a 3-inch refractor will allow you to use a magnification of 150, while with an 8-inch telescope, a power of 400 is possible. Your observations should be kept neatly in an astronomical notebook. The location of your observing site should be recorded, including the latitude and longitude, if at all possible. No observation is useful unless it carries the observer's name, the time in universal time, or GMT, telescope, magnification, and seeing conditions. For this, the scale devised by the late E.M. Antoniadi is suitable. It ranges from 1, near perfect conditions, down to 5, very poor. Mars, Jupiter and Saturn are now on view, and with the total eclipse of the Moon taking place on April the 15th, in this month's programme we take a look at how best to make observations of the planets. There are two types of telescope: the refractor, which uses a lens to collect the light of the object on view, which is focused down the main telescope tube into the eyepiece, where the image is magnified. For planetary work, a 4-inch refractor is the smallest useful size, which is reasonably portable, larger refractors are superior, although better suited to being housed in an observatory. The reflector telescope uses a main concave mirror to collect the light of the object. There are two types: the Newtonian, which reflects the light of the object